Zwierlein come to visit us today. He's an expert in this area of Hubbard gases and so forth. Martin got his undergraduate degree from the University of Bonn and also the École Normale in Paris. And he got his graduate degree at MIT with Wolfgang. And he spent some time on postdoc in Mainz. And he joined MIT in 2007, where he's now holds the Thomas Frank Chair in Physics. His focus here is on strongly interacting quantum gases and molecules, which he's going to tell us a little bit about today. He's won lots of awards. Let me just name a few. A Young Investigator Award from ASOFR, from DARPA. He's the David and Lucille Packard Fellowship. And he's also II Rabi recipient. So, and we have to thank him because we had to negotiate this so his family would allow him to come. So his son and two daughters are anxious to see him back. But we're going to hold him hostage today, and he's going to tell us a little bit about Fermi pairs and loners and active Hubbard gases. Please, clip this here somewhere. Let's see, does this work?
Can people on Zoom hear me? How can people respond directly? Oh, wonderful. Oh, that's great. And I even had a pointer somewhere, which at the desk, yeah. Thanks so much for having me. I'll tell you about well, hopefully mostly happy story about pairs, but there's some loners and they're maybe unhappy in these Fermi gases that we trap in optical lattices. And the nice features that can look at every single one of these fermions. The spin-ups are maybe for your, well, maybe red, spin-downs are blue, and the doublons are purple. And this is sort of a cartoonist's impression of who might be married to whom. I'll tell you more about this story. So this is one part of the talk. Generally speaking, we try to, where should I stand? We try to create strongly interacting atoms in one way or the other. So either we can do this because the atoms happen to have a very nice collisional resonance, a Feshbach resonance between them, where you can make the interactions go through the roof, in fact, as strong as quantum mechanics allows. And that allows you to realize fermion gases in the bulk that are strongly interacting and even superfluid at low temperatures. I'll tell you a little bit about an update on this experiment in the following. We can also have fun rotating these gases. We can even rotate weakly interacting gases, like a Bose-Einstein condensate, spin it up and get it into the lowest lambda level by spinning it up. That actually means now that the kinetic energy is completely modified. You no longer have your p squared over 2m parabola that you know from free space, but you are now confined in one and the same lambda level of the ground state of cyclotron motion. And then the interactions again dominate the scene because you have quenched the kinetic energy of the system. Or you do it more sort of brute force if you want. You quench the kinetic energy by just trapping the atoms in an optical lattice. Now they're sluggish, and now again the interactions dominate. And I will tell you about this Hubbard type model in the main part of the talk. So let's first actually look at the superfluid Fermi gas. This is in free space. We have a nice container which is made out of light for these atoms. We love lithium-6, but you could do it with, for example, potassium-40. There are not so many choices where you have easily laser coolable and strongly interacting fermions, but lithium-6 is the workhorse in this field. And you can tune the interactions just using a magnetic field to make them either really strong, well, then these fermions form tightly bound bosons, and you get a Bose-Einstein condensate of molecules as the ground state, or you make a weakly attractive gas, and then Bardeen-Cooper-Schrieffer told us that you will still get a superfluid, but of long-range Cooper pairs. And you can easily tune in between just by tuning a knob in the lab, which is the external magnetic field. So for a long while now, we know that these gases are superfluid. At the time, we rotated the gas and observed the lattice of quantized vortices. But there are other ways to find that these gases are super. And so I will give you a little bit of an update on this type of experiment. Yeah.
What's the like the lattice. For BCS theory, you have a lattice of for the phonon. So what happens?
Beautiful. You don't need the lattice here. This is all in the bulk. All you need is a weak attractive interaction. That comes from, if you want the interatomic potential, at long range, it's always attractive due to the van der Waals interaction. And that's all you need to have an attractive gas of fermions. Now, the details are a bit more complicated. You need to know about the scattering length of this interatomic potential, and you want that to be negative, but ideally strong, so that you don't have to cool to ridiculously low temperatures. Otherwise, because if the interactions are very weak, yes, at 0 temperature you would get a superfluid, but the pair binding energy would be very small because of the very weak attraction, exponentially small, and you would have to cool extremely low temperatures. So Cooper pairs are fragile. So with these scattering resonances, we can make the interaction very strong and need to cool only to say 17% happens to be of the Fermi temperature, which is the degeneracy energy scale of these gases, similar to the BEC transition temperature that people knew how to achieve in 1995 already. So thanks to the strong interactions, cooling a Fermi gas to superfluidity is not harder these days than cooling a Bose-Einstein condensate. That was a bit too long an answer, but yeah, it's a great question. Yeah. So what have we done these days with this gas? These were just you just saw the heroes of the experiment. And what we did is creating sound waves in our gas, and we actually have a happy box. Unfortunately, it's not as large as the box that you see on the left side here. I would love to have that much lithium-6. That would be just amazing. I would probably swim in it. It would be fantastic. But unfortunately, we have a small 100-micron scale box made out of light. So it's a pretty pristine box. And the atoms spend most of the time in the dark, which is nice, and only sometimes they hit the walls and bounce back. So it's really quite an ideal situation, a uniform gas of these lithium-6 atoms. But then the experiment is precisely what's happening on the left side. We just shake, one of the walls by just modulating the intensity of the laser beam on the left end cap here, and that shakes the gas. So this is the cartoon, what's supposed to happen. Let's see whether that actually happens in the lab. Well, you see it's very faint. Something is happening. Let's subtract the two images, the shaken and the unshaken one, and then you see, yes, you actually get very nice density modulations in the gas. And you see how they travel in space. And importantly, you see how they get damped in space. And that is what we were really after in this experiment, because the damping of sound tells us about the viscosity of the fluid and the thermal conductivity of the fluid. So these are interesting transport coefficients that we were after in this experiment. And so here's a plot of the sound diffusivity of this strongly interacting Fermi gas. Very hard to calculate theoretically. So there are some two sort of estimates are in green and orange of some theories that try to estimate what this should be. But it's extremely difficult to make any quantitative theory because the interactions are so strong. But in the experiment, you get these transport coefficients with error bars. And well, I could tell you a little bit about why these things go with certain power laws. That's maybe not so interesting. What is interesting is that at low temperatures, there is a limit of diffusivity, which is just expressed in terms of Planck's constant divided by the mass of the particles. That's a universal sort of bound for diffusivity. And hilariously, if you look up the viscosity and sound diffusivity of helium-4, which is a boson, you also find that it's on the order of h bar over m. So that's quite of a kind of a nice connection, even though this is a Fermi gas. Because of the strong interactions, it behaves in a universal way, giving you this quantum limit of diffusivity. But there's sort of a sad part of the story. The red line here is where the gas is supposed to become superfluid, and we saw all these nice vortices, etc. But there's nothing special happening in this sound mode diffusivity, not at the scale of these error bars. So what's actually super about this superfluid? It is the thing called second sound. The idea came from Laszlo Tija.
Martin, before you go on, could you go back to the previous slide? This is Bill.
I hear you. I knew it immediately.
Okay, now
so nice to have you.
It's good. It's clear that the diffusivity is going to a constant value as you go below some temperature, but it's not going to h over m. So is there any theory as to what the coefficient should be in front of this?
There's no theory that is quantitative. No. There's estimates which are like these orange and green lines. There's some better theories which go a little bit lower, maybe to 0.3 and capture what we measure in the experiment. But there is no one who can actually tell you quantitatively with any reliable theory, with any reliable error bar, what the value is from theory. So far, you have to ask the experiment.
Okay.
Can I follow up on
Oh, please, yeah.
So, well,
Good to see you.
Yeah, good to see you.
Oh, yeah, good to see you.
Sorry, I'm late.
Don't worry.
So, anyways, you're talking about strongly correlated part, but also there is a weakly interacting Fermi gas, and for that, viscosity was actually calculated by Khalatnikov back in the 50s, I believe. And there is, in fact, a formula through.
Yeah.
Did you compare what you get with what you're supposed to get?
Nope. So we did the experiment pretty much only at unitarity at the strongly interacting regime. It would be super interesting to go to the weakly interacting Fermi gas. I have to say that then we also have to work much harder to cool to really be in the case where we have a very nice degenerate Fermi gas to work with. Where so.
Degenerate. You get classical fluid. It also has viscosity. Viscosity is not a quantum phenomenon.
Yeah, and this you see already at the high temperature regime. So now let me explain this. So this is simply coming from when you take just the scattering cross section and the density, and you say, okay, so my diffusivity is roughly like the typical velocity of these guys times the mean free path. Mean free path is 1 over the density and 1 over the scattering cross section. And at high temperatures, since we're at unitarity, the scattering cross-section goes like the de Broglie wavelength squared, which is 1 of the temperature. And then you have still the velocity in there, which goes like square root of temperature, which is why you get t to the 3/2. So this limit can be calculated, and it's actually the black line with exact prefactors, no problem, because it's a classical gas, absolutely no problem. And we asymptote to that regime. So the classical gas sort of, you could say, is basically, I wouldn't say checked off, but like we're like confident that it works out. But what you're saying is even more interesting, to go to the really low temperature Fermi gas regime, ideally on the BCS side of things, and repeat the experiment, which we haven't done. It's very nice, very, very interesting to do so. Oh, yeah, maybe. Okay, so since I had all this formula, so at low temperatures, why h bar over n? Because now you have the velocity being limited by the Fermi velocity, which is just given by h bar over m and the interparticle spacing. That's just de Broglie. He would have given you that. If you have a wavelength of the interparticle spacing, you get h bar over m d of the velocity. Mean free path is as short as it can possibly be, because between these atoms. So it's also the interparticle spacing, which cancels out, and you're left with the h bar over m as the diffusivity, just to make you feel good about the scale. So now what's really, I will not go through my talk. Okay.
Yeah, sorry about that, but previous
this is more
slide.
important, right? We want to teach something.
So you told us that this high temperature limit, the T over TF to the 3/2 power, was essentially a classical limit.
Yeah.
But it's got an H bar in it. So what's the sense in which it's classical?
Yeah. So the TF also has an H bar in it. So we have to see. So the relation between the scattering cross section and the temperature is the de Broglie wavelength squared, which has H bars in it, right?
Yeah.
So it is only semi-classical in the sense that we are here at the scattering resonance, and in the most naive, classical theory would get probably some infinite scattering cross section, which it isn't. It is unitarity limited by the de Broglie wavelength squared of the scattering process. So now you get density times mean free path velocity times mean free path, which is velocity over density over de Broglie wavelength squared. So now the velocity has a h bar in it. Sorry, the velocity has no h bar in it. Sorry, the de Broglie wavelength has the h bar in it. It's and that's why you get this h bar in front. It comes from the de Broglie wavelength squared setting the scattering cross section.
Okay. Well,
Okay.
let's move on. We'll
Do you see the screen? You don't see when I paint on this thing, right? No. Okay. Okay. Are you satisfied? Okay, so the Broglie wavelength
we'll come to
squared
it later. Otherwise,
h bar squared over mkbt. It's cool. and the velocity is square root of kbt over m. That's great. So that means there is a h bar left over, and it's the origin is really the unitarity limited scattering cross section.
Yeah. Well, maybe at the end we'll read this.
Yeah. So in that sense, it's quantum, but only for the purposes of giving you a finite scattering cross section. Once you have that finite scattering cross section, which is quantum, you get a classical gas of colliding particles. It's kind of a cool limit. So now here's the super thing about superfluids. It's the second sound. So Tisha and Landau, they taught us that, in fact, in this order, Tisha 1938 and Landau 1940, sort of pretending not to have read Tisha's paper. Well, okay, not quite right. But there are actually two sound modes in this gas. Why? Because you have two fluids. The idea was to have a normal and the superfluid mixed together. And when you have a mixture of two fluids, you get two sound modes. And what happens is that these two sound modes are, on the one hand, the first sound, which is the sound we just saw. It's a density wave where normal and superfluid oscillate in phase. And there is an entropy wave, second sound, which is a heat wave, where heat propagates like a wave. And here normal and superfluid oscillate out of phase. And this was actually in 1944, beautifully demonstrated by Peshkov in helium-4, where he actually saw the second sound mode below the critical temperature of superfluidity. So let's see whether we can actually make some experiment to see the second sound. We need a thermometer because we need to look at heat, not at density. How can we get a thermometer in our cold atomic gas? Well, all we need is a spectrum that shifts with temperature, pretty much like the black body spectrum from Planck's law. Here we have another spectrum. It's a radio frequency spectrum of these gases. It's not that they give it off, but we can actually try to rip a spin out of our interacting gas, put it into a non-interacting state, and that costs some energy difference. If it was completely in free space, we would know with atomic clock precision, Bill could to tell you exactly what would be the RF frequency to throw in. But if the spin is attached to the soup of others, and ideally maybe it's even paired up with the others, then it takes an extra amount of RF energy to move it out of the superfluid. And so you see from high temperatures to low temperatures, these RF spectra shift, and that is all you need for a thermometer. I don't even need to calibrate my thermometer if I don't want to. If I just want to see second sound, I can just sit at one particular frequency and watch whether the local signal is high or low. That's the idea. So here are just three cartoon spectra for a cold gas, for a hotter gas, and a super hot gas. And we great. Okay. The hottest should be on the left, but doesn't matter. And so this gives you a spectral response that is roughly linear in temperature. It doesn't even have to be linear in temperature, but it is over a range. And here down here you have a cartoon picture of how you could imagine it working. It doesn't need the cartoon. I told you we just need something that depends on temperature. But if you want to have a cartoon picture, you could say the superfluid pairs, they're tightly bound, and it would take a large RF photon energy to break them. So if you tune your frequency to these loners, then you only transfer the lonely spins that are not paired up. And once you take a picture of these, you have taken a picture of the local entropy. Pretty cool. And it actually works. Here we have a gas where you see the density being pretty boring. but the temperature is not boring. There is a temperature gradient written into this gas. On the left side, you have hot. On the right side, you have cold. It's a thermometer with sub-nanokelvin precision, where you can actually see locally what happens in the gas. And why locally? Because we can do this RF transfer and immediately take a picture of the transferred atoms, and that gives you a local thermometer. Yeah.
What is the time scale? What's the collisional time scale? And what's the speed of sound? I guess it's the time for the speed of sound to cross the sample.
Beautiful. So like the typical frequency of the sound is like 10, 20 hertz. So it goes very slowly through the box. And the collision time you asked is this unitarity limited, sort of, it's like 10 kilohertz. It's on the scale of the Fermi energy. They really collide like mad. So always maintaining local equilibrium very efficiently. I wonder, maybe your question is also about timescales of the RF, and whether now, as you have transferred these spins, you have to worry that they might walk around and diffuse. And you do have to worry about that. You have to take this picture quickly after, otherwise you get a diffusion of your flipped spins. Absolutely. That's maybe part of the question. Yeah. Mm-hmm. So let's throw this thermometer onto our gas after we have created a second sound wave. So this is not looking at the density, this is looking at the heat. And the point of this amazing movie, very pixelated, is that if it starts again, you see it starts, they start hot on one side, yes, red down here, and they trade places. Now it's hot on the other side, and back and forth. And here you see the movie as frames integrated over the boring direction. So you see how they trade places, and heat really sloshes back and forth in this gas. It's quite slow. I mean, look at the time scales. It takes like 50 milliseconds to reach the other end of the box. It's a slow speed. And here you see that it's really super. In a normal gas, above the critical temperature of superfluidity, you just have boring diffusivity of diffusion of heat. So you make a hot spot in your coffee or whatever, it will simply diffuse like heat diffusion, and that's the end of the story. Once you cool below the critical temperature of superfluidity, you start seeing beautiful second sound waves in the superfluid. And that's a quite nice way to pinpoint the superfluid transition of this gas. We also saw one thing that was unexpected, at least to us, and again, there's no quantitative theory we can apply here. Namely, what does the diffusivity of second sound do as a function of temperature? It looks much more interesting than the first sound diffusivity. You see there's a dramatic peak of the second sound diffusivity, which is the damping of the second sound. And in the normal fluid, it would be just the thermal conductivity of the thermal diffusivity of the gas near this critical temperature of superfluidity. This is actually expected if you look at helium-4. They, with much smaller error bars, see a beautiful divergence, near divergence of the diffusivity of second sound as they approach the critical temperature of superfluidity. So in that case, this could be directly fitted with the universal behavior near second order phase transition. So it's a critical fluctuations that cause you this damping. For us, I'm not daring to fit any power law here, but at least qualitatively we see this strong dependence of the second sound diffusivity near TC. At low temperatures, you might ask, why does the second sound diffusivity go up again? Actually, same thing happens in helium-4 again. That's when the gas becomes very void of extras, loners that you can scatter with, and your only excitations are phonons now. They're sort of very inefficient at re-equilibrating locally the gas, and it drops out of being hydrodynamic, which always means the diffusivity goes crazy, and at some point you will turn into a collision-less gas whose damping will eventually go to zero, actually. It's a complicated story, but yeah. Maybe as a takeaway, this gas of lithium-6 and actually the sibling potassium-40 are on the map of Fermi gases or Fermi substances the strongest interacting superfluid with the highest critical temperature compared to its density. Now, to put it here on the same plot with high temperature superconductors and all kinds of other stuff, my colleagues, this is Pablo Herrero doing twisted bilayer graphene, had to multiply all numbers by 10 to the 8. But you see, these atomic gases come closest to the BEC critical temperature of any of these Fermi systems. And the thing we usually say is superconductivity would already occur far above room temperature if you had electrons that were interacting that strongly. So there's hope, one day maybe someone finds a high TC room temperature superconductor at ambient pressure, please.
Actually, we find them every week, so that type of moderator.
True.
Every week we get announcements.
Yeah, exactly. Yeah. I know. It's crazy. The other one from last summer was amazing. Yeah. Yeah. So, why did they put it? Well, okay. This is not a Fermi gas. This is sort of. So these guys just put all kinds of interesting superfluids on there. Indeed, helium-4 is a complete outlier. These guys also called our gas something different. I think they called it BEC or something. So they didn't quite get things perfect. I mean, it's like 5.
Do they have helium-3?
They should, but in that case, it would probably not on this scale. I'm not entirely sure. Helium-3 is a weakly interacting Fermi gas, and its critical temperature is like a promille of the Fermi temperature. So let's see, even if they scale it up for TC to be roughly here, okay, then the Fermi temperature would be, it could be slightly outside of the scale of this graph. It would be to the right here. Yeah, because it's such a weak interaction that the binding is very weak and fluffy, and so you have to cool much more. Okay, let's now go to the lattice system. I will spare you all the other stuff. I'll just try to make a bit more close contact, who knows, maybe, with high TC superconductors just by the fact that these live on the lattice. So when people studied these high TC superconductors, they were wondering whether maybe the simplest model could capture them, which is the Hubbard model. It's just electrons hopping on a lattice from side to side and interacting whenever they are on top of each other. In fact, they interact repulsively because the electrons don't like each other. And so that's an interaction term in the Hamiltonian. Very simple. So kinetic and potential energy. And you would think this problem must have been solved a long time ago. But no, one cannot at the moment solve it exactly for all parameters. There are special cases where we know exactly what happens, like at half filling. If you have 1 electron per site, we know what happens, that it's an antiferromagnet, which is nice. It makes direct contact with the interferromagnetic parent compound of these high TCs. But going away left and right, doping extra electrons or putting some holes, suddenly there are no known techniques that give us the complete phase diagram down to the lowest temperatures. It's kind of an amazing problem. If you followed chess yesterday, that happens on 8x8 lattice. It's completely out of the question to do that in exact diagonalization. You can maybe do 4x4, but 8x8 is absolutely impossible. So yeah, maybe we should challenge the chess players to help us out. That would be amazing. Okay, so this has been a long story in cold atoms, starting, of course, with the Bose-Hubbard idea in 1998, Jacques Zoller-Sirac, but then spilling over into fermions. And there are lots of experiments. I stopped at some point populating this graph, I guess in 2021, because I ran out of space. So I'll tell you maybe the recent thing about directly observing fermion pairing in these gases. And the nice feature compared to the story before is we can here see every single atom in the experiment. So that's the nice feature. Here you see what happens with the repulsive Hubbard model. As you go from a sort of intermediate coupling regime where the interaction is actually quite strong to a strong coupling regime where you have very strong repulsion. You see the gas sort of organizes in a special way. The density looks interesting. The bright yellow, those are the doubly occupied sites. and the orangey stuff is singly occupied atoms. So we can see both singly occupied and doubly occupied sites here. And what you see here in the middle is 2 atoms per lattice side. That means you have formed a band insulator. And outside here, you have singly occupied sites. That is a Mott insulator. The atoms still insulate because they don't want to hop onto each other. They don't want to hop on top of each other because the interactions are so strong. If you weaken the interaction, now there's much more motion available. And it looks like a hot soup, but it's not a hot soup. It's just a strongly correlated Fermi gas. And out of these pictures, you can get a lot of information. Of course, macroscopically, you see what the density does as a function of potential height. This is all happening in a trap. So immediately you know things like the compressibility and the pressure, and you can get at the equation of state of this system. On the microscopic side of things, you can actually check that you actually filled in fermions and not bosons accidentally. Could have happened, right? There's potassium-39, potassium-41. Here we use potassium-40, because you see that around any spin-up fermion, there's a Pauli hole, an exclusion hole, where another spin-up atom is much less likely to be found, over a scale given by the de Broglie wavelength again. You also see interesting excitations of this Mott insulator, doublon hole excitations, where you have lots of neighboring pairs of doublons and holes. And of course, a single image, maybe it's a fluke. No, if you repeat this experiment 50 times, you can do beautiful statistics and back out these doublon hole correlations.
So the low density there doesn't change very much, but you see the pairing concentrating a bit the center. What determines the outer boundary of that cloud?
Right. So it's precisely this interaction strength U. If your local chemical potential is enough to overcome the repulsion of 2 atoms, then they say, like, okay, we can now go on top of each other. So if the potential energy is enough to suck them onto the same lattice side, then they're like, yeah, okay, let's do it, even though we hate each other. So the U is not infinite, it's just something. And once the local chemical potential is too weak, like in the edges, they're like, let's stay away from each other. That's why in the center you have this nice doubly occupied region, and then in the outskirts you have the singly occupied Mott insulator region. It's a measure of the local chemical potential. What I'm not showing here, what I should, is the underlying trap, which is roughly harmonic, doesn't have to be harmonic, which scans the local chemical potential through the cloud. Yeah, that's nice because in one shot you get basically the equation of state of the gas. But this talk, I was wondering, where's Bill? Yeah.
Now, if these were bosons and we saw the picture on the right, we would just say, oh, this is the usual wedding cake structure that we're expecting from a Mott insulator. We've got occupation 1 around the outside. We've got occupation 2 on the inside. But you've described this, which is fermions, of course, as being a Mott insulator on the outside and a band insulator on the inside. Could you explain the difference?
Right. So the band insulator has no more room for additional fluctuations. So we cannot have, for example, a third particle hopping onto a given lattice side, leaving a single particle on the neighboring site. So a 3-1 fluctuation is not possible because we have used up all we can if we limit ourselves to just the lowest band in this optical lattice, where we have a spin up and a spin down atom available. For fermions, that's all that can be done. And the band insulator is therefore then full and in some ways a bit boring as a state, right? Because it's just like I'm just filling all I can into this box. So there's no more room for fluctuations. Whereas for bosons, of course, there would be, again, room for fluctuations. You could have 3-1 fluctuations of an n equals 2 bosonic Mott insulator.
Right. And in principle, if you had enough atoms, you could have a 3-tier wedding cake. Fermions, you can't.
Exactly. You can't unless you have so much energy that you can actually go to the second.
Right.
Yes. By the way, which we have to be careful about in the experiment, there is a second band, right? And we actually have to carefully clean out that second band so that we don't have additional fermions where they don't belong. That's actually kind of important.
How close does you get to the band space?
We can tune it so the band gap is like maybe on the order of 10 kilohertz or so, and we can tune it to be going through the roof. We can go to a resonance. I will say though that this is on the repulsive side, And usually you get instabilities once you cross, say, 500 Bohr radii or so, because the gas realizes, wait a second, there's a much more attractive state to live in, which is the attractive side of the Feshbach resonance. So we don't even want to crank up the U to be sort of unitarity limited. Yeah.
The experiment showing
How close with the U? Well, I don't know, 5 kilohertz, something like that. We tune, I mean, it's tuned through here, right? We could go to the band gap, but then actually we would have terrible instabilities because the atoms would realize they would much rather be on the attractive side of the resonance, attractive branch.
You get you like what is it on the right here?
I believe maybe 14 or something T. So and T is like 200 hertz or something like that. So then we get like 5 kilohertz or something like that. Did I do this right? Maybe not. 3 kilohertz. Don't. I'll bring my lawyer and give you the exact number for this picture, which we took before the pandemic, and I forgot everything that happened before the pandemic. Okay, good excuse, huh? So a few kilohertz and T is a few hundred hertz. Attractive Hubbard model is now what I really want to talk about, because this was the repulsive story, and you might think that's the most relevant for the high TC community. Sure, but there is another branch. Number one, it connects to the first part of the talk. Number two, there's a beautiful mapping between the repulsive and the attractive Hubbard model. Let me maybe walk you through this. So when you switch the sign of U to be attractive, now the guys again want to be on top of each other. They don't hate each other, but they love each other. So you can form tightly bound bosons again, and those should actually condense at low temperatures. So indeed, there is actually, again, a BEC-BCS crossover for the attractive Hubbard model, where you have a BEC of tightly bound bosons on one side, and then as you weaken the attraction, you again get this sort of Cooper pairing, very fluffy pairing of long-range Cooper pairs. And it's interesting in this BEC-BCS crossover that there is already pairing above the critical temperature for superfluidity. So that's unlike what happens in BCS theory. BCS theory happens down here for very weak interactions. The moment you form pairs, like in helium-3, you're also superfluid. But for us, for strong interactions, you can be in the regime where you first form the pairs at higher temperatures before then they can condense. These pairs are not trivial pairs. It's not just a molecule or something like that. It's not a two-body pair. It is heavily dressed by living in the soup of others. So it's a many-body pairing that happens in the strong coupling regime. So the lattice spacing is 0.5 micron.
No, I mean,
and
two-dimensional, three-dimensional.
It's a two-dimensional. It's two-dimensional. Yeah, it's a costed staulus, and it's this picture actually applies for a low filling of that lattice, because there's interesting stuff happening at higher filling, as I will mention. So a dilute gas of fermions in 2D, and it's costed staulus like indeed. On the right-hand side, I show you this very nice mapping between the repulsive Hubbard model that most of condensators are interested in, and the attractive Hubbard model. It's very simple. You take this, let's call those the spin downs, I don't know, and replace them by holes. And the spin ups you don't replace by holes. If you spin ups, you leave. That means a single down occupied site in the repulsive Hubbard model becomes a hole, and a single spin up site on the repulsive Hubbard model becomes a doublon. Right? It gets an extra spin down attached. Oops. And so you can, for every state in the repulsive Hubbard model, you can write down what the state would be in the attractive Hubbard model. So, for example, these Mott insulators that we have seen, where we have one atom per site, could be blue or red, might not yet be a spin-ordered Mott insulator. That turns into what's called a disordered charge density wave. Fancy way of saying you have lots of doublons, but they're still not ordered. They're just swimming around, leaving some gaps or sometimes not. As you go colder, you go to below the Néel temperature in this repulsive Hubbard model, you get a beautifully ordered antiferromagnetic state, up, down, up, down, up. That turns into an ordered charge density wave, where these doublons order like on a checkerboard. Think of yesterday. If you don't know what I mean, I'm like, I have no words. Okay. Here is, for example, other states like a D-wave superfluid, which is sort of a doped interferometric mod insulator, possibly happening in the Fermi-Hubbard model with repulsive interactions. That turns into a spin polarized charge density wave. So you have these doublons forming a checkerboard, and in between you have some single atoms mixed in that themselves order in interesting ways. So let's explore this attractive Hubbard model, but for that we really need to image not only the density but the spin of the atoms. And so there we had to work quite hard to make sure we can actually see each spin in our two-dimensional lattice. So what we do is we take this lattice and split it into two identical lattices. It's a bilayer now, and we make it such that the spin downs go up and the spin ups go down, or the other way around, however you want to label them. And now they're split by half a micron only, but we still can distinguish them. We can actually make sure that there's a node of the imaging light in one layer and only imaging the other layer, and vice versa. So we get an image for the spin ups and we get an image for the spin downs, and we can combine them to get the total density. So we digitize these images in the way on the right, where white means doublons, red and blue are the single ups, single downs swimming in the soup. Now we can explore what happens as we go towards attractive interactions. First, this is a non-attracting gas here. It doesn't look like much, but if you were to check the correlations here, you would already see the Pauli hole. You would already see that the reds don't like to be near other reds and the blues don't like to be near other blues because they're fermions. As you now increase the attractive interactions, pairs start to form. And of course, the stronger attraction you have, the more of these pairs you have. In this case, the white stuff are really these tightly bound pairs, right, where they're on top of each other, these doublons. You also see a glimpse of these charge density waves forming, like these local checkerboardy regions, which is what these pairs would like to do. They would like to order in this checkerboard phase. I'll say more about why and in a little bit. But so those are the images, and then you can have questions like, when do the pairs form and how do these pairs interact? So again, here's the same sort of phase diagram again, schematically, that we're exploring. The little sad wrinkle of my story is that our temperatures are roughly here, which means you see it's too hot to be superfluid. So we have not yet reached down to the superfluid regime in this 2D Hubbard lattice. But we are already in an interesting regime where you already have strong pairing correlations and also these charge density wave correlations in these images. So that's where we are. And the story otherwise is like we had before, this PEC-BCS crossover story. And we can check first things first, for example, that the doublon number increases with increasing attraction. We have seen this in the images before. So this is expected. The stronger attraction, the more doublons you form. And this agrees perfectly, by the way, also with theory that can still be done at the temperature range that we are at for this doublon density. Now let's look at the a particular image here for U of T of 8.4, which is quite relatively strong and strongly directing. You see lots of doublons. Again, I mentioned some of these guys form these interesting patterns. But you can ask, what are these extra singlons here sprinkled in, like the blues and the reds? Are they really loners, or are they actually just sort of part of a pair? And they could be part of a pair because you have actually this possibility to have a fluctuation from this local doublon of one particle, say the spin down, hopping to the right, leaving its spin up neighbor there, but of course in the next moment fluctuating back. In other words, the wave function of these pairs contains not only the doublon, but also the next neighboring pair. So of course, from a single picture, you cannot say that that's the case, but you have to do statistics, and we will do statistics in a little moment. I already pointed out many times the checkerboard that appears sometimes. Now let's go to weaker attraction. U over T of 6 is an interesting regime where the interaction strength is on the order, a little bit larger than the bandwidth of this lattice, and that's where you have these strong correlations that are very hard to tackle theoretically. And there again, you get lots of these singlons, and the question is really, are those just now uncorrelated fermions, or are they paired up? So I allow myself to actually draw this cartoon where they are paired up because we have done statistics on these images. Let me show you. We have to look at the correlations of these spins. We have to repeat the experiment, say 50 or 100 times per U over t, and ask, on average, when I find a spin up particle, what is the probability to find another spin up nearby? We already saw there should be a Pauli hole surrounding like fermions, and that's exactly what you see when you don't have any interactions. But when you now increase the interactions, it's this correlation region grows, and you start to have a larger region where the spin ups really would much prefer having a spin down nearby than a spin up. And this is actually the combination of having the Pauli hole and attraction between these particles. And in this very strongly interacting regime, you're back to the simple picture where the interactions are so strong that I can at most have a small fluctuation to the neighboring side and very quickly coming back. In other words, you have a very small admixture of the wave function of just hopping to the neighboring side. That's why you see the correlations become very short range. But again, of this sign that you expect that the ups want to be near the downs, which is really this picture down here in this cartoon. So now let's identify the pair formation here. We take these images, we look in a virtual box that we draw, and we ask, what is the total magnetization in this box? If you have a paired gas, the magnetization is always 0, because every spin up has a spin down partner somewhere in this box. If you have an uncorrelated, unpaired gas, then there is Poisson noise. So once you find the total magnetization is always 0, great, you know your gas is paired, even if these pairs might be a little bit longer range. So that's what you can do. The professional way to write it is you look at the total magnetization fluctuations of this gas. And now if you remember your STEMAC, that is directly related to the spin susceptibility of the gas. And when that turns 0, you have a pairing gap. So let's just look at this total fluctuation as a function of interaction strength. And you see it goes to 0 at a particular interaction strength for our temperatures on the order of U over T of 6-ish, where therefore we know over here on the right-hand side, we have a fully paired gas. And on the left-hand side, we still have some loners fluctuating about. Yeah.
How big is the square you look at, because there are edge fluctuations?
The absolute edge fluctuations, and of course we have to be very careful about it. The square is what you see actually. This is what we use. So we have to be careful not to go too large also, because we have a little bit of a trap still on. So then we would integrate over regions that are at a different density, right? That's an annoying thing. And we also have to be worried about integrating just noise and getting some offset, which is actually the case. One has to carefully do error correction to not the fancy one, but just to make sure you understand your detection errors. We don't detect with 100%. We detect with a few percent error, each spin up and spin down. So you have to be very careful in doing this sum of the correlators in order not to get some crazy offset or something like that, right? So that's a very good point. Yeah. Yes.
What about pairs that get cut by the box?
Exactly. So that's now a little bit, you're squeezed from both sides. If you're too cold, well, which is usually a good thing, your correlation length might be larger. Maybe you could actually see pairs that are quite large, who knows? But then, you would run into this trap issue. So you could say, luckily, at our temperatures, the correlation length is short enough, and the pair size is not so long that our box is sufficient to grab the entire contribution from the spin fluctuations.
So am I really expecting a transition here, or is it
No.
like activated behavior?
Activated behavior, it's exponential. Yeah, so it looks like sudden, but this is not a critical interaction strength. It's just activated. Yeah, and at 0 temperature, everything would be 0. Even on the left-hand side, I would have everyone paired up, so I would still have 0 total spin fluctuations, even for the weakest attractive interaction. Very hard to get there because temperature is exponential. Yeah.
sneakily looks like a point that's off the curve, but it's not one of the data.
Sorry, what?
The legend on the bottom left, that's not a data point.
Oh, yeah, okay. Okay, maybe not an excellent placement of a legend. Thanks for pointing that out, damn it. Okay, yeah. Yeah, that's just a legend. Oh God, okay, yeah, great. Thanks. Yeah. We'll fix that. One point to make is that the pairs are many-body pairs. What do I mean by that? The interparticle spacing, you have basically seen it in the pictures, is roughly 1 lattice site. But this correlation, due to the pairing, extends over more than 1 lattice site. Not much more than 1 lattice site, but to 2, maybe not quite 3 lattice sites. The point is that the pair wave function is heavily modified by the presence of these other fermions. In fact, it makes the pair smaller than they would be in isolation. If you had an isolated spin up and spin down on the lattice, you could actually do the math exactly, and you would find it quite a large pair, given by the interaction strength. That binding energy would correspondingly be very small also for this 2-body pair. So actually, the pairing is helped by the presence of these others, which sort of tucks in the pair wave function to be a little bit narrower, but still, as you see, larger than the interparticle spacing. So that's why we say it's actually a many-body affair and not just a 2-body pairing that we are seeing. Good. So we also saw this checkerboard phase. That's looking at the density correlations of the gas. So when you just look at density fluctuations, what do you see? If you have a big density hump somewhere, then it's very likely that the next site will be empty, and then there's yet another hump 2 sites over, and so on. So you see this checkerboard, and that means these pairs like to order. And you can also see it in the Fourier transform of this density correlator. Gives you a nice peak at pi. That simply means it's a checkerboard. So quite a nice sort of, if you want, signal that something interesting is happening in the charge sector. Why are they doing that, these pairs? Well, they do want to spread their wings. We saw that. They would like to sometimes be able to fluctuate to the next side, so profit a little bit from the kinetic energy and then come back. But if there's already a pair on the other side, I cannot fluctuate there because there's already a spin up there. So I will be more squeezed, so my kinetic energy is increased, and I'm not happy. So that's why they really want to spread out as much as possible. And well, if you have roughly 1 atom per side, the best they can do is to form this checkerboard lattice. It's actually very interesting. It's sort of a competing phase, if you want, to the superfluid, which is another way that they can exist, which is sort of a state where at every site you don't know whether you have a doublon or you have a hole. It's kind of a beautiful superposition of a doublon and a hole. And at exactly half filling, those states, the superfluid and the charge density wave, are completely degenerate. So an interesting order parameter that is actually 3D, if you want. And we shouldn't be surprised because it's just the mapped version of the interferomagnet on the repulsive side of the story, where I have an X, Y, or Z interferomagnet as the ground state. And it so happens that the Z interferomagnet that maps onto the charge density wave, and the XY interferomagnet maps onto the superfluid phase. It's a bit too much information, but it's kind of a beautiful story. That's without interactions. If you don't have interactions. Yeah. Good. So now we can just follow this through this crossover, if you want, increasing the interaction strength and seeing that there's a sort of a peak near the regime where you expect the strong correlations to be strongest. That's nice. And maybe one more thing to mention is that we can actually know the temperature of our gases by directly looking at the fluctuations in the gas. We don't have to ask theory help or something. We can actually just look at the fluctuations and the compressibility of the gas, which we directly get for free in our trap. And together they give us the temperature just through the fluctuation dissipation theorem. So compressibility is directly related to temperature and density fluctuations, which is kind of nice. So we know our temperatures are a little bit higher than 0.3 T and a little bit higher, unfortunately, than the predicted TC, which is around 0.2 times the tunneling. Oh well, it's always good to have more goals to go after. So I don't want to saturate the story. I will skip the story of this polaron and just want to show you one picture of what happens next. What happens next is so okay. Summarizing maybe that would be nice. So now I cannot find the play button. Okay, great. And then I can
More.
there's a super cool way to hide this hide floating meeting controls. Yeah, what the pandemic has taught us. So this is sort of a summary of what you have seen on the Hubbard side of things. You can tune the interactions between repulsive and attractive and go from a regime where you have these Mott insulators, band insulators, strongly coupled metals, to a regime where suddenly these fermions love each other and form pairs, and these pairs themselves even start to order in interesting ways. So it's a beautiful sort of phase diagram that we can explore. You could say, oh, we're too hot at the moment. Yeah, we're not too hot. We're actually in a very interesting regime where you have all these fluctuations, and already that makes it hard to make theory, to do theory. I'll say a bit more about that. And what you have seen on the left-hand side, these spin pair fluctuations are actually, if you think about it, just a dual version of these double on hole fluctuations I mentioned in the beginning. That's precisely what happens under this mapping. The double on hole fluctuations become up-down broken pair fluctuations on the attractive side. It's kind of beautiful to see this duality. What is next? And that's just a teaser for the future, not for the next hour, because I will stop here. It is what happens with when I dope more spin ups into the gas than spin downs. Now there will be lots of loners, which will be unhappy, and you have interesting phases predicted. For example, not just the superfluid phase, but an interesting phase. It's called Fulde-Ferrell-Larkinov-Chinnikov phase of a spoonful superfluid, like a magnetized superfluid, which sounds like an oxymoron, something that doesn't work, like black milk. But it actually does work, at least on paper, and no one has seen it. And we should try to see whether that works out, that you get a superfluid, but the extra loners, they order in a beautiful kind of a crystal. So we have started looking at that. Here are some pictures of the attractive Hubbard model with spin imbalance, where you see I chose blue for the majority. I don't know why. It's a Fermi C of these blue guys coexisting with these doublons as bosons. It's a very interesting Bose-Fermi mixture where you have hardcore next neighbor repulsion, because these bosons don't want to be near each other, and the fermions don't want to be near the bosons usually. There is actually a transition that we saw where the fermions do start to love sitting next to the bosons, which I think is a glimpse of the something to happen at lower temperatures, but we're not sure. So that's just telling you where we are going right now, and I'm just out of time to tell you more. So I'll just thank my group for the wonderful wonderful work, and you for your attention. Thank you so much.
Questions? More questions? But you can make a comment. You shouldn't be so apologetic of the temperature being not low enough. This is really great.
Thank you. It is a bit funny that all the groups seem to be roughly at the same temperature. We hoped on the attractive side we would get colder. I still have that hope. We are colder than we used to be on the repulsive side, but we also fixed a lot of things, like changed some noisy power supplies into good ones. So I cannot promise that it was because we went to the attractive side. I think the attractive side was attractive because it is the lower branch of this Feshbach scenario, right? You have a repulsive branch, an attractive branch, and the attractive branch is the ground state from the atomic physics perspective. So that's why I hoped we would get colder. We haven't been fully rewarded yet, but we also found out that our piezo drivers do some crazy stuff. And last week, and we'll just throw them back into the trash and see what happens. Yeah, maybe it gets better.
general question about this very beautiful food counting statistics. We have access to a lot of data.
Yeah.
So I was wondering whether there is a more agnostic way to process it, meaning that you don't have any model in your head in terms of correlation length, etc. You scaling with temperature, and then extract everything from that, and then look at the scaling rather than choose like a specific size of the box, length, etc. One of the things, for example, I saw in the big plot that you showed is that you summed over all the correlation lengths, and then higher and higher you go in correlation, more noise from you.
Exactly.
Have you thought about that? Is there a way to kind of?
Well, I would claim we're trying hard to be agnostic. We're trying hard to be agnostic as we can. So we know our noise. So we know how far we can hope to allow ourselves to go with the correlators, right? For example, this thing, right? So we know our noise, so we know how much trust to put. We can have error bars, and there's no model that is sort of underlying this, right? There's also the other thing that we have the model-free thermometry that I showed a few. Actually, let me maybe I have some extra slide on this model-free thermometry, which is.
You don't need to even look at the two-port correlation. You can look at all kinds of.
Oh yes, so that would have put me to talk about this polaron stuff. We have actually looked at higher order correlators, and it's very interesting. You can actually ask, what happens when I know I have a spin on one side? How does that affect the charge density wave order across it? That's the story I skipped. If you go to even higher order correlators, you need to take more data. But yeah, in principle, we can actually just suffer and just take a lot of data and look at higher order correlators and in these systems. One quick thing on the agnostic stuff. So what I really like is this fluctuation thermometer. I already mentioned, you look at the compressibility and the fluctuations, and you get the temperature. So it's really out of a StatMech sort of book where you see a linear relation between the fluctuations and the temperature. And as you heat the gas, you actually get more fluctuations for the given compressibility, higher temperature. So it's nice. Just one example how we actually try really to not look at any theory. And in fact, for the theory comparisons for the imbalance gas, which I couldn't show, we gave this to the theorists way before they had their code, and then it lies on top of each other. That's the goal of quantum simulation. It's not the other way around, where we sort of know the answer and we just, oh, okay. Yeah.
So, I have a question about this spin counting. So I think it's really simple and beautiful idea to identify pairing, but at any finite temperature, you have some distribution of quasi-particles which are unpaired.
Mm-hmm.
So, well, it's not like some fixed particle, it's some superparticles which appear and disappear. So what's your time resolution from this picture? Can you capture this fluctuating logarithmic sedation? I don't know if I'm making myself clear, but you find a temperature of some sort of single particle stuff that should still disrupt your total magnetization in a box.
Right. So I would be a bit careful. So the
time scale is very, I don't understand. Yeah.
Oh, time scale.
Yeah, because it's not like there's this electron and this electron that are unpaired.
So this goes into a beautiful story that I totally have 0 slides on because we're doing this right now. There is an interesting question about the time scale. If you have these longer range pairs, but they're sort of really correlated and love each other, then that means if you suddenly on some scale, not too suddenly, but sort of not too fast, not too slow, increase the interaction strength, they should go on top of each other into a doublon. And now we could take a picture and see the pairs as doublons. Turns out that works. It's kind of beautiful. So when you do this in a gas that doesn't look very correlated on first glimpse, once you do this ramp, suddenly you see a crazy charge density wave. I'm a little bit exaggerating if my excitement comes through, but it's enhancing quite significantly. For example, the visibility of this order of these doublons. So there is a time scale that we have to get at. We shouldn't be too fast because then we just project. We shouldn't be too slow because then we really go to the other phase, or maybe it's like in a more BEC-like. And so there is a time scale for that.
I'm sorry, I don't want to look into myself. I mean, my question is slightly different. So if you look at the superconductor, so it's not true that all electrons are paired. So you have classical just breaking up of Hooker pairs, which is fermionic distribution of the gap, and you also have quantum. So, but it's not. They're not individual. You know, these two electrons aren't paired. It's always changing.
Exactly.
So So the question is, are you able to see the excitations above the ground state, or is sort of average picture of the ground state? So can you see excitations?
Yeah. Well, first of all, we are at temperatures where we are unfortunately not yet even in this sort of mean fieldish BCS kind of ground state. Number one, unfortunately, right? In principle, you would be able then, if you were cold enough, to see these excitations. There would be a coherent admixture, though, at 0 temperature. There would be coherent admixture to your gas. And however, let me just think. You talk about quantum fluctuations or thermal? It sounds like you're doing quantum. Yeah, thermal for sure. That would actually give us this non-zero total magnetization. That means you have broken pairs. You have broken pairs, and that means they swim around. You see them fluctuate, so that total magnetization fluctuation would not be 0. In other words, the spin susceptibility would not be 0. Yes, because those guys now could flip their spin if it wasn't charged particle in magnetic field. Right. Quantum fluctuations, everything is so coherent. That's why I'm a little bit wondering whether this would just still. It should actually give 0. It should give 0. But dynamics would be cool. You could do something like sudden change of view and then probe, something like that. Sudden change of view and then probe. Yeah. That's roughly going the direction of what we're trying to do at the moment, to try to glue these pairs together to get a nice measure in one shot of the pairs. This needs 50 shots, but if we glue them together, we need 1 shot. So that's why it's super nice to glue them together into a doublon, take a picture, and then look how they are ordered.
Sounds like a discussion we should hopefully have.
Yeah.
Yeah.